this video, we're going to solve the January 2023 Unit 2 from AS Physics. So let's start with this video, but I will actually download the paper from my website. It's very easy to identify or find out my website from Google. You just need to type edexceleasy.com and that will lead to the website. Now in this website, you can find all the recent question papers. The internet is not connected. In this website, you can find all the recent question papers, including the locked ones and also the mark schemes. And they also give you an idea about what batches are still open under this institution. So let's start. I'm also trying to update this website by including the chapter-wise question papers or maybe formula booklets for physics and maths and notes for this part. Okay, so we're starting with A-level physics today, so we'll move to physics and we're going to solve the January 2023 paper. So clicking on the files will lead you to a Google Drive and you can find the question paper that you want to solve or you want to find out. So let's download this paper first and then we'll solve the entire question paper. Okay, so this is the January 2023 Unit 2 AS Physics paper. We'll move on to the questions very fast. So in question 1, it says the graph shows how the current I varies with the potential difference V for our electrical component. Each of the component is represented by the graph. We know that we saw 4 IV graph, one for the thermistor, one for the filament bulb, and one for the diode, and one for the resistor at fixed temperature or constant temperature. Now, if I recall all the graphs that I have taught for the IV graphs, the first one was, this is for the filament. Just like this, the opposite would be for the thermistor. Right, this is for the thermistor. And for diode, it was like this. Right, now the graph that they have provided is for a resistor at a constant temperature, because a resistor that obeys Ohm's law at a constant temperature, the resistance will not change. You can find out that the gradient of this graph, the IV graph, would give you the value for your resistance magnitude, and along this entire graph, the value for its gradient is constant, or you can also consider that the value of the resistance is constant. So this is for a resistor at fixed temperature. So option B is the correct answer. Moving to question 2, the monochromatic light travels through air and enters a glass block. Which of the following quantities does not change as light enters the glass block? So even though it is referring to monochromatic, it just asks you about the causes of refraction. Now in refraction, what happens that from air to glass medium, when light enters the glass medium, its speed obviously decreases, its wavelength decreases because it moves closer to the normal line, its direction changes. Another thing happens is that the amplitude gets shorter. Okay, so the only thing that doesn't change for a wave property during the cases of refraction is its frequency. The frequency always stays constant. So if you write the equation V equals to F lambda, frequency is constant, and if velocity decreases, wavelength also decreases, as they are directly proportional according to the equation. So option B is the correct answer over here. I hope question 2 was clear. We'll move to question 3. A ray of light approaches a boundary between air and glass as shown. The angle of incidence is I. And which of the following statement about total internal reflection is correct for ray of light at this boundary? Okay. Total internal reflection cannot take place. TIR takes place if it is equal to critical angle, if it is greater than critical angle, or if it is less than critical angle. Now, for usual case, we would select option C as the correct answer because obviously total internal reflection can only happen when the angle of incidence is greater than the critical angle, right? But over here, as the light is traveling from less dense medium to high dense medium, so the laws of the total interreflection were that light must travel from high dense to low dense medium, right? In this situation, it is not traveling from high to low. Instead, it is traveling from low to high. So obviously, the first fact does not actually satisfy. So we cannot consider that even if the angle of I is greater than critical angle or not, total internal reflection cannot occur at this boundary because light is not traveling from higher medium, it is traveling to lower to higher medium, right? So total internal reflection cannot occur at, even if the value for I is greater or less than or equal to critical angle. We'll move to question 4. The equation n lambda equals to d sine theta can be used to determine the wavelength of laser light that has passed through a diffraction grating. Which of the following is represented by d in the equation? We know the small d represents the distance between two adjacent lines on the diffraction grating screen, and it's a diffraction grating filter, and there was another d included into this equation referred to diffraction grating, that was capital D. Capital D was for diffraction grating. Sorry, capital D was for the distance between the diffraction grating and the screen, right? So these are the two distances, capital D and small d. So we can obviously understand that option A would be the correct answer, right? Not the other options, and also not the distance between the zero order and the first maxima or consecutive maxima distances. So no, all the other options are wrong. Option A is the correct answer. We move to question 5. A bat is an animal that locates objects using a pulse echo technique. A bat emits a pulse of sound wave that travels to an object. The bat detects this reflected pulse 6 milliseconds later, and the speed of sound is 340. Which of the following gives in distance in meters of the object from the bat? Now over here, obviously this is an example for the reflection or echo case. Let's say if this is the bat and there's an object over here, the bat emits a sound, so it travels a distance d, and then it gets reflected back to the bat's ear, so it travels twice the distance. Sorry, we were in this question. Sorry, no, we were over here. Okay, so it travels twice the distance, right? So like d in the forward direction and d in the backward direction. So there's actually twice the distance traveled in this section. Okay, another thing over here that we can find out, the value for t is already given. Now the value for t was for this entire two distance situation, right? The 6 seconds, 6 millisecond was required by this bat to travel two distance time. So let's use the equation, the basic equation for echo, which would be Vt by 2, right? D equals to Vt by 2. The value for V was 340. Now we can clearly see that they haven't changed the values for the speed in any of the options, right? So we'll take the V as a whole and we'll take the T by 2 as a fraction. So which is basically 6 into 10 to the power minus 3 over 2, and that becomes 340 into 0 0.0 sorry, 10, two zeros over here, like this one. This is how the overall arrangements of the data would look like. So option B in that case would be the correct answer. Sorry, option C. I'm really sorry. Option C would be the correct answer, as you can match the answers from this calculation and the MCQ parts. Okay, I think question 5 was clear. It was quite easy to understand. We move to question 6. A light-dependent resistor is connected in a circuit as shown, and the intensity of the light incident on the light-dependent resistor decreases. So which row of the table is correct? So these rows are entirely about the ammeter and about the voltmeters, right? So over here, The voltmeter is connected to the fixed resistor and the ammeter is connected to the entire circuit. So when this LDR, the intensity of the light being shown to the LDR decreases, we had to turn off the recording for a while because there was a flying cockroach. Whatever, we'll just continue to question 6. In this situation, they want you to find out that how the voltmeter reading and the ammeter reading changes when you are emerging or using a light with lower intensity for this LDR. So in this situation, try to recall the relationship between resistance and in intensity for the LDR, as intensity and resistance are inversely proportional over here. So when you actually incident a light with lower intensity on the LDR, the resistance of this LDR would increase, right? Which means now the overall circuit has a higher resistance, right? As all the components are connected in series, so the RT would be total like the total resistance for this entire circuit would be equal to the resistance of each of the components. Since the fixed resistor, the value for the fixed resistor is always same, it cannot change. But in case for the LDR, now with a lower intensity of light being incident on it, the resistance would increase. If the value for the resistance of the LDR is increasing, then obviously the total resistance for the entire circuit would increase. And according to the equation of V equals to IR, we can write V equals to 1 by I dot V, which is basically indicating that resistance and current are inversely proportional. So if the total circuit's resistance is increasing, the total circuit's current flow would also decrease. So the ammeter will show a lower reading, or the ammeter reading will decrease. So we can clearly understand that out of all this, only option A and C could be one of the possible correct answers, because it refers that a decrease in current reading, right? Now, in case for the voltmeter, again the fixed resistor and the LDR are connected in series, which means that if the resistance for the LDR has increased to a higher energy level, or increases to a higher amount, the voltage requirement for this LDR would also increase, as both of the components are sharing the total voltage from this cell. Now as LDR is going to receive, or is going to take more of the voltages from the cell over here, so less voltage will be available for the fixed resistor. So which means the voltmeter reading for the fixed resistor would also be less, because most of the voltages are being used by the LDR. So the voltmeter reading would also decrease, which means that option A is the correct answer, right? Ammeter reading decreases as total resistance in the circuit increases, and voltmeter reading also decreases because the voltage requirement for LDR increases, that causes a decrease in the voltmeter for the fixed resistor. Okay. I hope question 6 was clear. It was quite tricky, as the information was provided before the LDR and the requirements were provided for the entire circuit and for the fixed resistor, right? So we'll move on to the next question. I hope 6 was clear. Question 6. The diagram shows some of the energy levels in an atom. The electrons in this atom are excited from the ground state to the energy level N3. Okay, so like most of the electrons were initially at the ground state, and then light was incident on this atom, and the electrons received photons, and they were excited from the ground state to the level 3 or N3. Now, how many different frequencies of radiations can be emitted from these atoms as the electrons return to their ground state? So after being excited to a higher energy level, obviously the electrons cannot stay there for the entire time. They need to fall back to the ground state. So when they fall back to the ground state, they will certainly release some kind of radiations. And during this time, how many radiations can be expected from this kind of labelings, or this kind of energy levels? So one radiation could be from directly from N3 to N1, another is obviously from N2 to N1, and one would be from N3 to N2, right? So there are 3 possible frequencies of radiation that can be emitted by the electrons of this atom. So option C is the correct answer. We'll move to question 8. When longitudinal waves pass through a material, compressions and refractions are formed. Which of the compression following statement is correct? Option A says that compression are points where the displacement of particles is a maximum. Now, displacement means that particles are being vibrated vertically. But in case of this situation, the particles are not actually never vibrated vertically, right? For longitudinal waves, the particles always vibrate to and fro, which is basically horizontally. So displacement cannot occur for both refraction or compression. So obviously option A is not the correct answer. Option B says that compressions are points where the pressure is a minimum. It is wrong. It is a point with the maximum pressure. So no, option B is also not the correct one. Refractions are points where the displacement of the particles is a minimum. As we have already mentioned that in compressions and in refraction, in case for all the longitudinal waves, there is no displacement for the particles. So obviously A and C are wrong for both the definitions of compressions and refractions. Last point, refractions are points where the pressure is a minimum, which is completely correct. Compressions are the points where the pressure is maximum, and refractions are the points where the pressure is minimum, which means option D is the correct answer. A lamp is connected in the circuit as shown. The cell has negligible internal resistance. In 30 seconds, the charge passing through point P is 0.4 coulomb. Which of the following gives the energy in joules transferred by the cell during this time? Most people confuses in this situation. They try to connect time with this. Okay, so they try to make an equations of that look like maybe equals to VQT. But there's no such equation like this. The main equation that we taught in our AS sections are E is equals to IVT, where you can certainly pair up the IT together, which becomes charge, right? The definition of charge was current into time. So this becomes charge voltage. So you can make an equation for energy transfer in joule with charge and voltage, which is QV or VQ, both are correct. And the value for Q in this situation was 0.4, and the value for V, which is basically the EMF of the power supply 2, is 1.5. So according to your equation, the answer should be option B. And VQ equals to VQ. Okay, we are done with question 9. We'll move to question 10. Which of the following is not a correct statement about stationary waves? All points between two adjacent nodes are in phase. So let's just draw a diagram for this to explain it. This is the original one and this is the maybe reflected one. Now over here between two adjacent nodes, which is points on this section and on this section. Right, all points between between two nodes are in phase. Now in this situation, in the next situation, all the points will move down and all the points will move up. Right, so you can clearly see that this is node 1 and this is node 2. So all the points between two adjacent nodes are actually in phase. So this is correct, right? This is true. And all points of maximum, amplitudes are points of maximum amplitude. Yes, these are the points of these are the points of antinodes with maximum amplitude, right? So these are antinodes, antinodes with maximum amplitude. So this is also true. The distance between two adjacent node is equal to one wavelength. No, the distance between two adjacent node is equals to half of a wavelength, right? We can clearly see the total wavelength was this, and between two adjacent nodes, we're just working up to this, which is basically half of the wavelength. So this is not true. This is false. And obviously this is the wrong statement for the adjacent for the stationary waves. So option C is the correct answer. I'll explain option D. The net energy transfer along a stationary wave is zero, which is true. On a stationary wave, no information is getting transferred, so no energy is getting transferred for this situation. So yeah, net energy transfer along a stationary wave is certainly zero, which means that option D is also not correct. Is also not correct for this situation because it is a true statement for the stationary waves concept. Okay, so we're done with the section A of Unit 2. We'll move to section B of Unit 2. A particle traveling at a speed of 9.89 into 10 to the power 5 millisecond has a de Broglie wavelength of 7.37 10 to the power minus 10 meter. Deduce whether this particle has an equal mass to the electron mass. Okay, so in order to find out the mass, we actually find you have to use the statement that they have provided, the de Broglie concept. Now they have provided the wavelength, that means we can find out the momentum using the wavelength and Planck's constant. So the basic equation was actually lambda is equals to Planck's constant over wavelength, sorry, over momentum. So we will make the momentum quantity the subject of this equation because we want to find out the mass, and mass can be found out from this momentum part. So it will look like Planck's constant over wavelength. We can break down the momentum using mass into velocity. So mv equals to h Planck's constant over wavelength, and just take that velocity to the left hand side. It will be Planck's constant over lambda dot velocity, right? So now input the values together and you'll get the value for the mass of the particle, and then you can identify that if it is equal to the mass of an electron or not. So mass is basically 6.63 10 to the power minus 34. Planck's constant, the magnitude for Planck's constant should be memorized. They would certainly give this at the end of this paper, but it's easier for you to memorize and do the working at a faster rate. Okay, so if you multiply all this together, so the value you get is 9.1 or 9.09. You can approximately write 9.10 into 10 to the power minus 31 kg. The mass of an electron was 9.11 into 10 to the power 31. And this is 9.10, right? So you can consider that it is similar to the mass of an electron, right? Not exactly same, but similar. So you can write that mass is similar to mass of electron. Me can be used for mass of electron, but this is not a mark scheme word, obviously. So question 11 is done. I hope it is clear for everyone. We'll move to question 12. In an experiment to determine the refractive index of a glass, a student directed a ray of light towards a glass prism. The ray of light is shown before and after entering the prism. Determine the refractive index of the glass. Okay, you can find out the refractive index as this is angle I and this is angle R. So refractive index is basically sine 32 over sine 50. That is 0.69, and this is the refractive index value for this glass prism. Maybe I'm making a mistake. Wait. Sin I by sin R, yeah. Ah, we need to find the angle from the normal, not from the surface area. Sorry for this inconvenience. In this situation, they are not giving you angles from the normal. You're supposed to draw the normal over here. I was trying to understand that why they gave 3 marks for this easy question, because of this reason. So the angle of incidence is actually this one, the light making an angle with the normal, not with the surface. It was making an angle with the surface 50 degree, so it will make an angle of 40 degree with the normal, right? Because the total angle is 90. 90 minus 50, that's 40. And over here 90 minus 32, that becomes 58. Sorry for this. So sine I over sine R, that would be sine 58 over sine 40. Okay, now you get a value of 1.32. Okay, 1.32 over here. Okay, so we'll move on to the next question. We need to draw on the diagram the ray of light as it emerges from the prism at A. No further calculations are required. We know that in glass prism the density is more, and outside the prism the density is low. So in this section we can also draw a normal over here for this second medium. When the light again comes in contact with the boundary, and it obviously has to be perpendicular to that medium too. This kind of looks perpendicular to that second medium when the light again comes in contact with the glass prism. So in this situation, as the light is now traveling from more dense to less dense, so it will increase its speed, increase the wavelength, right? Increase the amplitude. The frequency would be the same. So it will now move away from the normal. So during refraction, when you move from less dense to more dense, it moves towards the normal, and when it is moving from more dense to less dense, it moves away from the normal. So it will move away from the normal in this pattern. Sorry for this. Okay, and no need to draw the second normal over here, but I just draw it for the explanation purpose and also for my own convenience. Okay, so we'll move to question part B, I guess. A different prism is made of glass with a refractive index of 1.63. Calculate the speed of light in this glass. Okay, so we can use the second equation for the refractive index concept, which was refractive index equals to speed of this light in air divided by the speed of light in this new glass medium, right? So the equation kind of again looks like this: n1 speed 1 equals to n2 speed 2. As we already know, the value for speed 1 would be the value for light in air, which is basically 3 into 10 to the power 8 meters per second. And the refractive index for air is also 1. So we just need to find out the value for speed 2 in this situation, which is basically the speed of light inside this glass medium. Um, so if you arrange this equation, speed 2 would be n1 dot speed 1 divided by n2, where n2 is the refractive index. Okay, sorry, where n2 is the refractive index for the glass medium. So we can write 1 multiplied with 3 into 10 to the power 8 divided by 1.63. So if you calculate this, you get one. Okay, it's quite a big value. So 1, 2, 3, 4, 5, 6, 7, 8. 1.84 into 10 to the power 8 meters per second. So this is the final answer for question 12. I hope it was clear for everyone. Moving to question 13. Equal lengths of two copper wires W and Z are connected in parallel in a circuit as shown. The wire Z has twice the diameter than wire W. Explain why the drift velocity of the charge carriers is the same value in wires W and Z. Okay, let's first identify that these are connected in parallel, which means that they do not have the same voltage. Sorry, they do not have the same current, right? In parallel circuits, they have same voltage but different current. In this situation, the voltage is not a concern for us, the current is a concern. So you can write I is same or equal for both W and Z. And then another thing to identify over here is that the cross-sectional area, since drift velocity area are related, the first equation that should arise to your mind is I equals to NAVE. So in this situation, everything is same except for the cross-sectional area. The cross-sectional area for this Z would be pi d, yeah. So let's start with the W1. If the diameter of the W is just d, then it will be pi d square by 4, right? But for the case for the wire Z, since it is twice as thick than wire W, so it will be pi d square. Okay, because it's 2d over 2 whole square, the 2's gets cancelled out and you're left with just d square. So then if I try to find out the overall equations for I in this situation, sorry, I again wrote the wrong thing. Voltage is same, current is not equal. It depends on their voltages and resistance in along this over wire shapes. Okay, so let's draw. Let's find out the equation for the wire W. I equals to N A V E. Since we're trying to find out the values for drift velocity, so let's make V the subject. It would be I over N E, and A can be broken down in terms of pi d square by 4, right? Which is basically pi d square by 4, and this entire thing can be further written as 4I over NE pi d square. So you can write this down again as V is equals to 4I over NE pi d square. So this is the expression for the voltage of wire W. Then we can do the same working. Okay, we actually have a lot of space at the end. I'll do the entire calculations over there very neatly so that it's easier for everyone to understand. We have W, then we have Z. The area on this section is d square over 4. So the equation would be I over NE pi d square by 4, which is further on a simplified versions can be written as 4 dot I NE pi d square. Now I can make a similar type of equation for wire Z, which is area for this section would be just d square. So it will be I over NE pi d square. Now in this section we can clearly understand that the drift velocity for the W is 4 times the drift velocity for the Z according to our calculation. Now over here it needs us to explain that why the drift velocity of the charge carriers is same for both the wires. Like in our calculation it is 4 times the drift velocity than Z, right? Like all this expression is same. So you can write that this is the velocity for W, that is 4 times the drift velocity for Z. Now why is it the case that the question says that it is same for both the wires? That's because of the parallel combination. As for the parallel combination, as you can clearly see that as Z has a greater cross-sectional area, which means that it has a lower resistance, right? It has a greater area, which means lower resistance and more electrons can flow across it. And smaller resistance means that it has a greater current flowing through it. So it has a high amount of R flowing through it. But in the case for the Okay, so in this situation, for the wire Z, we have a higher cross-sectional area which indicates lower resistance and again which indicates higher current. So for a larger amount of current or larger magnitude of current, drift velocity obviously has to increase, right? So V this time would increase than its mathematical or calculated value that we calculated. Now, in case for the W, we can already see that we already have seen over here that this drift velocity for the wire W is 4 times, mathematically 4 times the drift velocity for the wire Z. Okay, now if this was a combination for series, then we could have easily said that, sorry, that then the drift velocity for wire W is 4 times the drift velocity for wire Z. But since they're connected in series, the lower magnitude of the drift velocity in wire Z is compensated by a higher value of current in the wire Z. So we can now write that they both have the same drift velocity, as wire Z has a greater cross-sectional area, which means smaller resistance, and has a greater current. And according to the equation, I equals to NAVE, for a greater current, the drift velocity of the wire Z will also increase, and thus will become equal to the drift velocity of wire W. Has greater cross-sectional area with smaller resistance be high, and so current would also be high, and wire so current would also be high, and this would compensate for the value of drift velocity. For the drift velocity, therefore they both have the same drift velocity or equal magnitude. So the overall working is done for 13A, explanation is done. We'll move to the next question, 13B. Now they're connected in series, and we need to complete the table by placing a cross in the correct box for each quantity. Okay, now the current in the wires, since they're connected in series, so obviously the different cross-sectional areas are not a big fact. The current is same for both W and Z. Since they're connected in series, voltage would be different, current is same, so both are same. Resistance of the wire, obviously the wire with the smaller cross-sectional area will have the larger resistance, so larger resistance for W, so this is the correct statement. And potential difference across the wires, again the higher the resistance, higher the voltage. So if wire W has the higher resistance, wire W will have the higher voltage. And drift velocity of the charge carriers in these wires, this was the calculation that we did for the previous question, right? We did found out that the drift velocity for wire W was 4 times the drift velocity for wire Z. That means drift velocity for the charge carriers in the wire is larger for wire W. So this is done. We're done with question 13. We'll move on to question 14. A student set up the circuit shown to investigate the properties of a negative temperature coefficient thermistor. Negative temperature coefficient thermistor indicates that with an increase in temperature, the resistance would drop, or vice versa. Okay. Now in this situation, the power supply has negligible internal resistance. We need to show that the voltmeter reading was about 6 volt and ammeter reading was about sorry, the information is given in the question. The ammeter is an given information. The ammeter reading is 23 milliamps. Okay. Now we are just concerned about this parallel combination over here, because the voltmeter was only connected across this parallel combination of these two fixed resistors of 500 and 600 ammeters. As all the components in this circuit are connected in series, so they all have the same amount of current. So we want to find out the voltmeter. So the current across this entire parallel combination would be 23 milliamps, because they all have the same current connected in series. So we can write the total resistance for this section. Again, the total resistance will be using the formula for the parallel combination, because 500 and 600 are connected in parallel. So we are writing RP, okay, resistance combination for parallel. We have 1 over 500 plus 1 over 600 So when like on the other side, you get 1 over RP is equals to 11 over 3000. So then you get 3000 by 111. The final answer should be 272.72 or something that continues. So we'll just write the resistance for this parallel combination is 273 ohms. Okay. I hope you guys can understand that we need a cross multiplication over here, but I'm not adding the cross multiplication in this working section because we do not have much space. Okay, now the main concern for this parallel combination was the voltage requirement. The current is already given 23 milliamps, so it will be V equals to IR, that is 23 into 10 to the power minus 3. We obviously need to convert the milliamps to ammeter and, and then multiply the resistance to it, which is 273 with this value. And if you calculate this, you're supposed to get 6.2727. So we'll just write 6.3 volt, which is obviously close to 6 volts. So option 14A is correct. We'll move to part 2. Calculate the power dissipated by the thermistor. Okay, so for the thermistor, we need to find out either the resistance of the thermistor or the voltage. It's easier to find out the voltage because if the total voltage provided by this power supply was 12 volt, and out of this 12 volt, if 6.3 is being used up by the parallel combination, then obviously the leftover um, available for the thermistor, right? So we can write resistor for thermistor, that would be EMF minus resistance for the parallel combination. Sorry. So we can write the EMF would be 12 minus 6.3, that is 5.7 volt. So this is the voltage for the thermistor. We already have the value for its current. So we can use the equation V equals to IV, the easiest one, 23 into 10 to the power minus 3 multiplied with 5.7. So if you calculate it, the power dissipation is 0.01311 watt. You can just write 0.13 watt. So we're done with 14A2. I hope it was clear. Moving to 14B. The student decreases the temperature of the thermistor. We need to explain the effect of the temperature of the thermistor on the ammeter and the voltmeter reading. Again, this is exactly the explanation that we give for the question 6 of this paper. In that situation, it was for LDR, and this is the same case for the thermistor. So again, the voltmeter and the ammeter were not connected to the entire thermistor, right? The voltmeter was connected to the parallel combination and the ammeter was connected to the entire circuit. If you are um, if you are decreasing the temperature, right? Yeah, decreasing the temperature for the thermistor, as it is a negative temperature coefficient conductor. So obviously a temperature decrease would indicate that the resistance of this thermistor would increase. According to the equation V equals to IR, if the resistance of the thermistor increases, the voltage across this thermistor would increase, which means that out of this 12 volt supplied by the power supply, more of that would be used by the thermistor, which indicates that this voltmeter reading that is connected across the parallel combination will decrease because more of the voltage are being used by the thermistor, so less is available for this parallel combination of fixed resistors. So this would drop. And again, since the overall resistance of the entire circuit is now increasing, right, the thermistor can modify its resistance in this situation. So the thermistor's um, resistance increases, it indicates that the entire circuit's resistance increases. And again, according to the equation V equals to IR, as the voltage for this entire circuit is constant, right? That is 12. The EMF is not changing. EMF is constant. So the voltage for this entire circuit is constant. If R is increasing, the resistance for this entire circuit is increasing, then current is again gonna decrease, right? I hope the explanation was clear. We'll move on to the working part. Okay, so let's write the answer that this would cause the resistance to increase, and that would increase the resistance of the entire circuit. The current reading would decrease or ammeter reading would decrease. So we can write according to this, current reading would decrease. Again, for the next point that sorry, for the next point that for the voltmeter, for a higher resistance, the voltage requirement would increase and less voltage is available for the parallel combination. So the voltmeter reading decreases. For higher resistance, voltage across thermistor increases and parallel combination decreases. And for parallel combination decreases. So we can write, therefore voltmeter reading decreases. Okay, so we're done with the question 14. I hope it was clear enough. We'll move to question 15. In this section, it indicates that a student connected a signal generator with the with loudspeaker. The student arranged metal plates in front of the loudspeaker as shown. The student left gaps between the metal plates. The gaps are obviously important because it causes diffraction to occur. The sound waves from the loudspeaker passes through the gaps. The gaps were approximately the same size as the wavelength of the sound, which means the same size indicates maximum diffraction to occur, right? The student stood at point X and heard a loud sound. The student walked to a straight line in the direction of the arrow. As her position changed, the sound became quieter until she heard no sound. We need to explain why the sound became quieter until there was no sound, and your explanation should refer to the interference, which obviously indicates that at point X, if she was listening to a higher or louder sound, obviously at point X, the waves from the two gaps are interfering constructively, so produces a maximum amplitude. And while she starts walking in the straight line away from point X, the waves are interfering destructively, where they cancel each other out and the amplitude is zero at that point, and that's why she doesn't hear any sound as she walk away from the point X. So this will be the possible answer. Another thing that we should include over here, because as this is a 6-mark question, so diffraction should also be a fact over here. So let's start our answer with the diffraction, that waves diffract as they pass through the gaps, and they diffract at the maximum way, or they spread out maximum because the wavelength and gap size are equal, right? So waves diffract as they pass through the gaps, and they spread out maximum because wavelength was equal to gap size. Okay, now we'll move to the overall explanations for the constructive and destructive interferences. Okay, so the next points would be for constructive and destructive interference. So we'll start writing from point X, that at point X, the waves interfere constructively with path difference of n lambda as they are in phase. So they produce sound with maximum amplitude. Maximum amplitude. I'm just writing A for amplitude. Okay, then we'll move on to the explanations for those points where the sound was zero or sound was entirely silence. So we'll write that as she moved away from point X, the waves interfere destructively with path difference n plus half lambda as they are in antiphase. So they produce sound with minimum amplitude. So this was the explanation for the 15A. Also, this was a star mark question, which means that in this question, your pattern of the mark scheme points will be judged, your language will be judged. So yeah, all these things will be a matter for it, or a matter for concern for this question. So try to arrange your answer in such a way so that all the mark scheme points are in logical pattern and written in good English. So we'll move on to the next question, 15B. It says that the interference can be demonstrated using visible light, and a student connects two filament bulbs to the same power supply, and a screen is placed at a distance from the gap. Um, Explain why it is not possible to create a consistent interference pattern on the screen using this arrangement. Because in this situation the lights are not actually incoherent. Coherent means that the lights needs to have the light waves need to be in phase, need to move with the same speed and all, same frequency, right? So they're not moving with same speed, they're not moving with same, I mean they are moving with same speed as light travels always with the same speed, right? But other than that they're not in phase and they're not from two coherent sources, so we cannot consider this as an example for interference patterns. So we can write lights are not coherent, or now you can write as they are phase relationship is not same at every point, the phase relationship would change. Okay, so lights are not coherent as phase difference is not constant. Sorry, is not constant. Okay, so we're done with 15B. We'll move to the next question, 16. Okay, this one says that An irrigation system uses a pump to move water from a lower level to a higher level. The electricity for the pump is generated using a panel of solar panels. The panel of solar panels is 1.2 meter long and 0.8 meter wide. To pump water from the lower level to a higher level, the pump needs a minimum power of 140 watt. We need to calculate the minimum efficiency of the panel of the solar cells that will operate the pump, and the intensity of the sunlight on solar cells is 1040 watt per meter square. Okay, so we can find out the value for the intensity of the sun, or like we can find out the amount of energy input in these situations, right? Because if the intensity of the sunlight on the cells is 1040, and we can find out the area using the length and width definitions, length and width values. So first try to find out the energy output, so energy input in this situation. The energy input means that power input in for this situation, right? So for power input, it would be intensity multiplied with the area, cross-sectional area. So that's I into cross-sectional area. I is the intensity of the sunlight, and cross-sectional area is 1.2 into 0.8. So if you calculate this, you're supposed to get 998 watt. Now out of this 998 watt, only the minimum efficiency required to operate this is 140 watt, right? Like the minimum power. So what is the efficiency of it? So you can find this out by using the efficiency equation. Energy output by energy input. Energy output was 1040, energy input was 998 multiplied with 100%, and that is 14%. So out of the 100%, only 14% is efficient in doing the work. Now for section 2, suggest two reasons why the value of calculated in 1 is the minimum efficiency that will operate the pump. Like it indicates that why out of the entire 998 watt, why only 140 watt is the minimum requirement for this to run the entire pump, right? That's because that not all of the sunlight is getting incident on the solar panel at 90 degrees. Some of the sunlights can be blocked due to the clouds or rain or fogs or any kind of weather um, problems. Another thing, that the pump itself may be not 100% efficient, right? We cannot blame the weather or sunlight for it. Maybe the pump receives the entire 998 watt but cannot use the entire 100% because of its thermal conductivity or other reasons. So we can write um, sunlight may not be incident on solar panels at 90 degrees. Another thing is that the intensity may be lower due to clouds. So I may be lower due to clouds. Okay, that's it. We'll move on to the next question then. 16b, B1 actually. Light from the sun arriving at the solar cells is unpolarized. Explain the difference between polarized and plain polarized lights. Polarized means that waves that vibrate in one direction, which is perpendicular to the direction of wave travel, and unpolarized means that waves that oscillate or vibrate in many directions. So the like basic related or like memorized definition for this would be unpolarized lights has oscillations in multiple directions, whereas polarized lights has oscillation in only one direction which is perpendicular to the wave direction of wave travel. So we are done with B1. I think this is actually a star mark question for us because this is a repeated question. You can memorize this answer and copy paste it for every question that asks for the definition of polarized and not polarized lights. Okay, moving to part 2. Describe how a student can demonstrate the light from the sun is unpolarized. Let's first understand that how this entire thing can be actually conducted. For example, you have solar panels over here, and you can find out that if the intensity is changing, then the power supply and everything would change, right? So you placed a vertical filter in this section. Okay, so when you're emerging sunlight through this vertical filter onto the solar panel, you calculated the intensity to be maybe 1040. Okay, approximately 1040. Now again, if you shift this, like now maybe you're like rotating this vertical polarized filter to a horizontal shape. Okay, now you're rotating this in such a way that now maybe it is in this pattern, okay, which is entirely horizontal this time. Now, when you have rotated this, if this sunlight was polarized, maybe it was vertically polarized. Okay, that's why while using the polarizing filter vertically, you got up intensity for light, intensity on the solar panel. But when you have rotated this solar panel by 90-degree at this section, then it should obviously cancel out all the vertically polarized waves of the sunlight, but in this case the intensity is still the same, which means that even if you're rotating the polarizing filter, the intensity is not changing. That means it does have vibrations in all the planes. That's why it doesn't cancel out the vibrations, or it doesn't decrease the intensity even if you are rotating the filters 90 degrees at each different orientation. So this indicates that the sunlight is unpolarized, and this is the experiment that the student can perform to determine the um, concept that the sunlight is unpolarized indeed. So let's just write that light, like the plane of the light can be detected using a polarizing filter, and after that if you rotate the filter, if there is no change in the intensity, then the light was unpolarized. So you can write that plane of sunlight is detected plane of sunlight is detected using polarizing filter, and if the polarizing filter is rotated, there would be no change in the intensity. Therefore sunlight is unpolarized. So in this section, obviously the answer, I would think there's not that much descriptive because it only contains 2 marks, and doesn't also actually explain the entire concept. I hope the overall explanation and the little diagram that I added helped you all to understand the entire concept for the entire experiment that you're supposed to conduct to understand if sunlight was polarized or unpolarized, right? So we'll move on to the next question, 17 for this paper. Students set up the circuit shown to determine the EMF and the internal resistance of the cell. I is the current of the circuit and R is the resistance of the variable resistor. So we need to show that for this circuit, R can be represented like this. So we can write it down as total EMF is equals to voltage of the fixed resistor plus voltage of the internal resistance. Now we can write voltage, like we can break down voltage in terms of IR. So we can again further write EMF is equals to I capital R multiplied with I small r. As I is common for the right hand side, you can take I as a common factor for I for the right hand side. Now just shift that I to the left hand side, and it will be EMF over I equals to R plus small r. Now again shift that small r to the left hand side, and everything would look like EMF by I minus R is equals to small r. So the entire equation would be R equals to EMF over I minus small r. But this is how the entire equation, like, this was just a shown kind of maths. So we are done with this. So we'll move to the next one. The student varied R and measured corresponding values of I. The student then plotted a graph of R against 1 by I as shown. So we need to find out the values for R and the values for EMF. According to the equation, if you like write the equation in this format, EMF over I multiplied with, sorry, minus R, it kind of resembles the equation of R equals to EMF multiplied with 1 over I plus minus R, right, which is basically in the form of y equals to mx plus c, which indicates that the gradient of this graph will be total voltage and the y-intercept is the internal resistance. If you go back to the graph, on the graph we have y-intercept at minus 2, which means the value for the internal resistance is minus 2. So value for internal resistance minus 2 ohms. And for the gradient, you can find out the gradient easily. Let's write two coordinates, 0, minus 2, and 8, 10. 8, 10. So let's just find out the gradient, 0, minus 2, 8, 10. The gradient for this straight line would give you EMF. So we're just writing directly as EMF. So we have two coordinates 8, 10 and 0, minus 2. So it will be minus 2, minus 10, then 0, minus 8, which is basically minus 12. This is 1.5. So EMF is 1.5 volt. We'll move on to the next question. The student suggested that the power dissipated by the internal resistance R decreases as the resistance of the fixed resistor increases. We need to comment on the student's suggestion and no further calculations are required. Okay, now power dissipation can be represented using the equation P equals to V square R, or for the fixed resistor it will be equals to V square capital R. Now over here, as capital R and small r, like the fixed resistor and the internal resistor were connected in series, which means that if the resistance for the internal resistor, if the resistance for this fixed resistor or variable resistor is increasing, then its voltage requirement will also increase. And as they're connected in series with a fixed power supply, like the power supply was only providing 1.5 volt. So if now the fixed resistor, the variable resistor is receiving the maximum voltage, it obviously relieves small amount of voltage for this variable resistor, which means voltage across the voltage across the internal resistance will drop. And according to the equation, P equals to V square R, since the value for the internal resistance is same, right? But the value for the voltage across the internal resistance has dropped down due to the voltage requirement for the variable resistor because of this large amount of voltage requirement across the variable resistor. That's why power dissipated would also decrease, and certainly the student is correct. So we can write this down over here that as R increases, voltage across variable resistor increases, leaving behind small voltage for internal resistor. And then according to the equation, P equals to V square R. As V decreases, P would also decrease. Right, which means the student is indeed correct. Then we move on to the last question that the students added a second identical cell in the series with the first cell and repeated the entire experiment. We need to add to the line and show the result on this experiment. Okay, since we are adding another cell or like similar cell, that means if the cell like the EMF, okay, like not EMF actually. I mean, yeah. If the internal resistance for one cell was 2 ohm, for two cells it will be 4 ohms, right? So the graph should start from this section. And another thing that it should be steeper. Like now the EMF should be greater than this one. So if the EMF is greater, for example, this time the EMF should be 3 because previously it was 1.5, now it should be 3. So we can find out one thing that the change in y-axis was 12 for that 1.5. So the change in y-axis should be a greater thing for this section, right? Okay, we can actually find out that where the graph would actually end its journey. For example, the change in y-axis for this line would be 14 in this time, right? Minus 14, because we know the initial point would be minus 4 and the final point would be 10. So we already got the y coordinates over here. And now the initial coordinate is 0. We need to find out the positive, or sorry, the final x coordinate where the graph would actually end. So you can find it out by using this kind of equation, that gradient is equals to 3 this time. I'm certainly sure that it is 3 because previously the EMF was 1.5. Since we are using two identical cell, 1.5, 1.5 becomes 3. On the y-axis, this time we have minus 14 reading. On the x-axis, that's missing. So you can find out x-axis by uh, 14 over 3, which is basically 4.66667, or you can write it like this, 4.6. Okay, so let's just draw a curve, connect the two dots together. Right, this is how you are supposed to draw a graph for two cells connected to this series circuit. And another thing, internal resistance becomes twice the previous one. That's why it got minus 4. And the gradient calculations is like this. We're not using negative values because the graph only has positive sections, right? And current is a scalar quantity. It doesn't have negative values. So even if your calculation gives you negative value, you should use positive sections in this section. We are done with question 17. I hope question 17 was clear. We'll move on to question 18, the last question of this paper. In an experiment, the demonstration of photoelectric effect ultraviolet light is incident on a metal plate. The photoelectrons are released from the plate with a maximum speed of this. We need to calculate the energy of these photoelectrons in eV, which means that first you find out the energy in joules and then divide it by 1.6 into 10 to the power minus 19. And that will just give you answer in electrovolt. So EK equals to half mv square, which is basically half. Okay, I'll just write this down as a whole. Okay, half mv square divided by 1.6 10 to the power minus 19. So half mass of the electrons 9.11 into 10 to the power minus 31 multiplied with the velocity they have already provided, 3.51 into 10 to the power 5 divided by 1.6 into 10 to the power 5. If you calculate this, it gives you 0.35 eV. Now we're moving to the second question. The table shows the typical values of work function for the different metals. We have informations for aluminium, magnesium, zinc, and iron. The ultraviolet light used in the experiment had a wavelength of 310 nanometer, and we need to deduce which of the metals are most likely to be to have been used as the metal plate, because obviously if you're using UV light and it is not enough, it is not providing enough energy, then there will be no emission, right? So we need to understand that if the energy is matching with your work function or is greater than the work functions of any of these metals, we can only use those, right? Not those whose work function is greater than the energy provided by our UV light. Okay, since at first we can find out the energy. At least the energy can be found out using E equals to HF, but as frequency is not provided, so we'll first find out frequency, which is C over lambda, right? Lambda is given. So let's just find out the equation as a whole in general. So the first equation that you're supposed to use is HC over lambda. This will give you the value for the energy, total energy. Another thing, the equation that you're supposed to use is total energy is equals to work function plus half mv square. As we are trying to find out the value for the work function for this metal plate, so you need to make work function the subject, and it will be E minus half mv square. Now the value of velocity is already provided in the first question, which was 3.51 into 10 to the power 5, right? So let's just use this final equation. E equals to, phi is equals to hc over lambda minus half mv square, which is 6.63 into 10 to the power minus 34 multiplied with 3 into 10 to the power 8 divided by 310 into 10 to the power minus 9, because it was in nanometers, and we need to subtract this half 9.11 into 10 to the power minus 31 multiplied with velocity was 3.51 into 10 to the power 5. If you do the entire calculation, you're supposed to get 5.86 into 10 to the power minus 19 joule. Okay, so you can clearly see that this energy's work function is very close to the work function of magnesium, right? So most likely it was magnesium metal. So we can write metal was magnesium. Okay. So we are done with the question 18A1. We'll move on to the next section of this question. Um, Question B. Photoelectrons are only emitted for a given metal surface if the frequency of the incident ray is above a particular value, and we need to explain why. Because each photon only interacts with one electron, and that one electron receives or absorbs energy from that one photon, right? So the minimum energy requirement for an electron has to be emitted should be higher than the frequency, right? So like if there are like more photons being emitted, then more higher frequency can be absorbed over here. So let's just write the answer that each photon only interacts or only collides with one electron, and that electron will absorb energy from those photons. And the minimum energy that is required for an electron to be emitted depends on that energy provided by the photon. And again, when the electrons jump or like fall back from that excited level to a ground state, they will emit radiations that has to be above a particular frequency. Okay, so just write the answer that each photon only interacts with one electron receives energy from photons, there is a minimum energy required. There's a minimum energy required for electrons to be emitted. Higher frequency. Moving to the last question of this paper, 18C. A student makes the following statement. It does not matter that what the value of the work function is for a particular metal. Photoelectrons can be released if the intensity of the incident line is high enough. Now, um, that's not actually a case. Intensity relates to the number of photons per second. Yeah, increasing the intensity would obviously indicate that maybe now more electrons are getting emitted, right? But in order for the electron emission to occur, it is always related to the frequency of the light that you are using. If the frequency does not match with the threshold frequency or is not at least greater than the threshold frequency, until then there will be no emission. Doesn't matter how stronger intensity you are providing. Intensity causes more electrons or more photons to be emitted per second, and if the intensity like if the light that you're using has a frequency greater than the threshold frequency, right? For that light, if you're increasing the intensity, then yeah, more electron emissions would occur. But if you're using a light whose frequency is smaller than the threshold frequency for that particular metal, then doesn't matter how much you increase the magnitude of the intensity, the frequency is greater is less than the threshold frequency, right? So increasing the intensity will not cause any emissions, even though you are now actually supplying more photons, but they do not reach to the threshold frequency, or they are not greater than the threshold frequency. So in that case, no emission would occur. So the answer should be that intensity causes more photons to be released per second, and it does not affect the energy of the photons. Intensity causes more photons to be released per second. It does not cause it does not affect energy of photons. Okay. So with this, our entire Unit 2 Jan 2023 is physics ends. I hope it was clear for every one of you, and if there is any question, please write down your questions in the comment section. I would try to answer those. And yeah, thank you for watching the video.